All right. Hello and welcome. This is going to be our very first video for the year. And to start out today, what I wanted to talk about was a little bit of a review from chemistry. So, while it's not required that you had taken chemistry before taking AP biology, I recommend it because especially in the first semester at the beginning of the year, there's going to be quite a few things that are going to go back to specific ideas that you would have learned in chemistry. And actually, our first unit, called the chemistry of life, is going to have to deal with some of that stuff. So, a good place for me to start is to go over some of the most important concepts that we should remember, both here in this first video, and the next video that has to do with the properties of water concerning things that you would have learned in your chemistry class that will be most important for you to be successful right away in AP Biology. Now, if you had just taken chemistry last year and did pretty well, or maybe if you've even taken AP Chemistry, this part you might be able to not spend very much time on. Because if you remember that stuff really well, there isn't going to be any kind of new chemistry in this. But if you especially have not taken chemistry yet, or to a lesser extent, if you're taking it right now, this is going to be very important for you to pay attention to. So, the first idea is that chemistry is the foundation of biology. This is, for some people, good news, some people, bad news. If you really don't like chemistry, the idea is there really isn't any escaping it. If you'd ever want to go on and study or major in a biological science like in college, you're going to have to take a fair bit of chemistry. For example, if you go to the UW and you'd be a biology major, you're going to have to take at least 4 semesters of chemistry, you know, because the chemical foundations of life give rise to all of the emergent properties of animal systems and systems of viruses and bacteria and systems of plants. So it's the very foundation that we build all of the rest of biology on, and that's why we're addressing it first. So just at the very beginning, remember that everything is made up of atoms. So all matter is made up of atoms, and everything is made of matter. So hopefully, even maybe if you haven't taken chemistry, this isn't anything that's brand new. Atoms made of protons and neutrons in their nucleus, and electrons which orbit around the atoms. In the Bohr model of the atom, I guess I'm getting a little in the weeds here talking about models of the atom, but I know some of you might call me out on, well, they don't really orbit, they're in orbitals, they're in probability clouds. I'm like, okay, for our purposes, the Bohr model of the atom is going to be perfectly sufficient. Here's the periodic table. So different kinds of atoms are different elements. In specific, though, in biology, we are only going to concern ourselves really with the elements that aren't grayed out. There are some exceptions, like when we talk about the nervous system. Even though chlorine is grayed out, it's very important with the nervous system um, and sending messages like that. But if you look at it, there's only a handful of elements here on the periodic table that are lit up. Those are the ones that are really going to be important for biology because they are found in significant quantities within living systems. Like I said, if I would change this, maybe I'll go back and edit for next year. I would take chlorine and I'd make that lit up too, just because I think that's an important one that we're going to talk about as well. So Unlike in chemistry, most of these atoms, these elements, are going to have nothing to do with what we're talking about. So we're going to focus in on these ones specifically. In general, life requires about 25 chemical elements. So 25 more than what's lit up here. However, 96% of all living matter is only made up of four: carbon, oxygen, hydrogen, and nitrogen. That makes up about 96% of all living matter. And then these other four, phosphorus, sulfur, calcium, and potassium, make up the large majority of the remaining 4%, something like 3.6% made up of these four. So 0.4% are made up of the other 17 elements that aren't on this page, right? About 25 elements are essential. We've got 8 here. So these make up the vast majority, all right? More than 99%. The other 17 elements make up less than 1% of the mass of living things. So this is something I would remember, all right? I would especially remember these four. You need to remember these four because they're going to come back when we talk about macromolecules. All right, especially what is going to become important right away is remembering how chemical bonds work, because that's going to be very important in macromolecules, and that's also going to be very important with the properties of water. So electrons, the electrons an element have determine its chemical behavior. The number of electrons in an atom's outermost shell, so its valence shell, dictate the chemical properties and behavior of an atom. So, as an example, in this picture of an atom, this outside shell or orbit, remember we're just looking at kind of a Bohr model of an atom, is the valence shell. Some people just call it the outside shell or the outside orbit. So that is all important. Hopefully that's something that remembered from chemistry because that was crucial in your unit on bonding. So why that's important is that all chemical behavior of an atom its reactivity depends on the number of electrons in an outermost shell. This one has 8. So it's going to behave very different. Can't even count. This one has 6. So it's going to behave very different from this one that has 2 in its outermost shell. Remember that if you were to look on the periodic table, right, 1, 2, 3, 4 elements in the same row have the same number of shells. So you can see the simple Bohr models drawn out here. All of them in the same row have the same number of shells. All of these have 1, all of these have 2, all of these have 3, right? Just things we're reviewing. I know that if you've taken chemistry, this is kind of old news, but I want to make sure even those people who haven't, they can kind of get this basic information. Then also notice that as we move from the left side of the periodic table to the right side, the number of valence electrons, those found in the outermost shell, increase. 1, 2, 3, 4, 5, and so on. So they're directly related, valence electrons, to the column an atom is in, and number of electron shells is directly related to the row something is in. Elements in the same column have the same valence electrons and similar chemical properties. All right, so all of the atoms in this row, since they have the same number of valence electrons, different number of shells, all right, but same number of electrons in their outer shell have same chemical properties. So why that's so important, it leads to chemical reactivity. Atoms tend to complete or fill their valence shells or empty a partially filled shell. So they either want their outside orbit completely filled or completely empty. And that drives chemical reactions because chemical reactions occur such that elements that have almost an empty shell can get rid of them, and elements that have an almost full shell can fill them. And they do that by creating chemical bonds or rearranging the distribution of electrons between elements so that they're all fulfilled by either sharing, right here, these atoms are sharing electrons, or gaining or losing electrons. So chemical bonds are really important in biology, and it's going to be very important here in this first unit on biochemistry, or the chemistry of life. So there are several different types of weak bonds. Hydrogen bonds, which I put in bold and red underlined because it's going to be extremely important. Hydrogen bonds are weak bonds. They're not very strong. There are weak attractions between elements. Hydrophobic and hydrophilic interactions, which we'll talk about in the next video, are very important. Van der Waals forces and ionic bonds are all weak types of bonds. And the fact that they're weak enables certain things to happen in biological systems that couldn't happen if they were strong bonds. And then really the only and most important form of a strong bonds are covalent bonds. These are stable linkages between elements that will also be important in creating the stability of biological molecules. So here's an example of a covalent bond. Just as a review, where sharing of electrons is occurring. Whenever I write, this is just a habit from chemistry, whenever I write E with a minus sign, that just means an electron. So, if covalent bonds are the main strong bond, then why is it a strong bond? Well, the fact is that two atoms share a pair of electrons. Both are holding on to them, so you would need to break the grasp of both atoms on those electrons to break the bond. It would be, maybe this would be an analogy. So if you just grabbed onto the arm of another person to try to hold on to them, assuming that you are both reasonably equal in strength, it would be a lot harder for you to maintain hold on that person if they were trying to pull away from you than if you and the other person would link hands. When you would grab the other person's wrist with your hand, and the other person with that same hand would grab your wrist to make that strong linkage, that'd be a lot harder to break than you just grabbing onto someone's arm. That's an example of why a covalent bond is so strong, is there's an attractive force between both elements, both atoms in that bond. Covalent bonds form molecules, so combinations of elements that are stable. So again, here's this picture. That is a covalent bond. Both of these atoms are sharing these electrons right here. They're in between both, they're being shared. And so there is, since the nucleus is positive, there's an attractive force. This atom is attracted to these electrons, and this positive nucleus attracted towards them here, these electrons too. So there's an attraction holding them together. Here's a molecule of oxygen where you can see there are two sets of covalent bonds. Here's one covalent bond here, hydrogen and oxygen. And here's another set of covalent bonds between hydrogen and oxygen. And so that keeps this molecule stuck together. So just like we had seen before, it's also possible to have multiple covalent bonds, so double or triple bonds. So two atoms can share more than one pair of electrons. So for example, here on this picture on the top, this is what's called a single bond, one pair being shared. Let's pretend that this is molecular hydrogen, two hydrogen atoms sharing electrons. But atoms can share more than one pair of electrons. If they share two pair, here's one pair, two pair, we call that a double bond, like in uh, molecular oxygen, O2. Or in some cases, we can form triple bonds by sharing three pairs of electrons. And a good example of that would be molecular nitrogen, N2. N2 has two elements, or two atoms of nitrogen, and here I'm just going to draw the Lewis structure of it. And they're sharing three pairs, so this is a triple bond. And so the higher bond order, triple versus double versus single, the stronger the bonds are. So a triple bond is extremely strong. When we talk about ecology at the end of the year, that's why we need nitrogen fixation, nitrogen fixers, to turn N3 molecular nitrogen into nitrates, because otherwise this compound N2 is bounded together so strongly that no biological system can use it like that. All right. I bring that up because bond polarity is going to be super important in our next video about the properties of water. All right. So this bond polarity has to do with covalent bonds. So this is covalent bonds that bond polarity has to deal with. Electrons that are being shared. So for example, in this picture, in water, oxygen and hydrogen are sharing these electrons. And in this picture, those electrons are drawn right in between the oxygen and hydrogen, right in the middle. And that works really well to get the idea that they're being shared, but that isn't accurate as far as what actually happens. Pairs of electrons that are shared in covalent bonds in a lot of the cases are shared unequally. What do I mean by that? That means that if I were to draw these electrons between oxygen and hydrogen more realistically, they wouldn't be smack dab in the middle. They would be closer, let's see, to oxygen than hydrogen. So I might draw them there, or I might draw them there. How do I know that they would be closer to oxygen than hydrogen? It's because oxygen has a stronger attraction for the electrons than hydrogen. Oxygen wants them, air quotes, wants them more. And that goes back to an idea from chemistry called electronegativity. Electronegativity is how strongly an atom, an element, will attract electrons towards itself. And atoms in covalent bonds that have a higher electronegativity than the other element that they're sharing electrons with will pull those electrons closer to itself, closer to itself. So, really electronegative elements are, for example, oxygen and fluorine and chlorine, all right? Elements that if you have your periodic table, elements that are farther to the right and farther up in the right corner are more electronegative. So up in the right uppermost corner, those are the most electronegative elements. So it's going to be important to just keep a reminder to yourself of where those are. All right. Water is what we call a polar molecule. What that means is that because oxygen is more electronegative than either of these hydrogens, the electrons that are being shared between this oxygen and each of these hydrogens are pulled much closer to the oxygen than they are to the hydrogen. If there's more electrons surrounding this oxygen, this end over here that's farther away from the hydrogens will become slightly negative, and that's what these mean. They mean that this side of the molecule is slightly negative because it's closest to the oxygen, which has more electrons. And this side of the molecule, where the hydrogens are slightly positive because the electrons are being pulled away, negative charges being pulled away from this side of the atom, so it's slightly positive. And any molecule where we can draw an imaginary line down it and separate it into a positive half and a negative half, just like the north and south pole on a magnet, we call a polar molecule. So water is a polar molecule because it can have I drew those backwards. I am so sorry. A positive half and a negative half. It is a polar molecule. Molecules that aren't polar are called nonpolar. Here is an example of a nonpolar molecule. Yes, carbon is slightly more electronegative than hydrogen, so these electrons will be slightly closer to the carbon side, but they're equal on all sides. I can't draw a line anywhere through the carbon to make a positive half and a negative half, or a positive side and a negative side, or a positive part and a negative part. So this one is nonpolar. And don't worry, because we're going to go over this a lot next time. This is just starting the concept of polarity. Oh, sorry. And then lastly, before we are able to move on to next time talking about the properties of water, the reason that I bring up polarity, the reason why I spent so much time on this is because it gives rise to hydrogen bonding, right? Hydrogen bonding is when polar water molecules create attractions between each other. The positive part of the polar water molecule, the hydrogen part, is weakly attracted to the negative part of another water molecule. This is what we call a hydrogen bond, and we represent it by this dashed or this dotted line between the oxygen in one water molecule and the hydrogen in another water molecule. And it occurs wherever OH groups exist in a large molecule. All right, so it doesn't just have to happen between water molecules. So I might write that down here. Not just between water molecules. So, for example, when we talk about nucleic acids, the base pairs in nucleic acids are joined together via hydrogen bonds. So, not just water molecules. The reason that these hydrogen bonds are so important that I was leading up to ending on this slide for today is hydrogen bonds give rise to all of the properties or important properties of water. And the properties of water are what we're going to talk about next time. All right, so that's it for our first video. I hope it's not too overwhelming. We will go over some of this in our live Zoom session. All right, but for now, if you have a question, just send me an email or a message or something. Otherwise, I will see you in a little bit.